Good. Well, it's a pleasure to have Gemma de la Cuevas today speaking about universality in spin models, automata, and neural networks. So the stage is yours, Gemma.
Okay, thank you very much, and thanks a lot for having me here. It's a pleasure to participate at QNLP this year as well. So as last year, I'd like to talk about some universality notions in spin models, automata, and neural networks, which I believe have a lot in common, and slightly beyond that as well. Yeah, I'd like to report on somehow the latest status of these ideas. So as last year, I'd like to start talking about the power of simplicity with an example which is well known, namely cellular automata. So if you have, imagine cells which can have two possible colors, black or white, and you have these very simple rules that you see on the left of your screen, I guess, where if the three cells on top have a certain pattern, then the cell in the middle below will have a certain other color. And you start with a very simple configuration where they're all white and there's just one black cell in the middle, and you start updating these things. Then, well, if you do it for 5 steps, for 10 steps, for 50 steps, that's for 100 steps, for 500 steps, you very easily see that very complex pattern arises. And in fact, this is used as a pseudo-random number generator in Mathematica. And well, what I'm showing you here is just the tip of the iceberg, as there are many other wonderful phenomena, very complex ones that can be reproduced with very simple rules, namely with cellular automata. But we also find a similar phenomenon in physics, specifically in spin models. Namely, if you take a spin model that looks simple, like the 2D Ising with fields, so it's on a 2D square lattice with pairwise interactions, Ising type, we find that the low energy sector of this spin model can behave as any other spin model, which includes very apparently complicated models, like models with many body interactions, with exotic symmetries, or things that you would consider to belong to a separate league. Well, all of this can be reproduced by this apparently simple-looking spin model. The same is the case for neural networks. So in a feed-forward neural network, which is essentially an Ising model, if you have a fixed architecture that is fairly simple and some interactions which are fairly simple, then this network can learn any function, which means that these visible units, the black ones, can behave as any other function you want. Namely, for any function, there will be a distribution of weights and biases, which are the coupling strengths of these hidden units, so that the black variables behave as you like. And obviously, the example I'd like to understand, but unfortunately, I won't have anything to say about it, is the one about the stunning complexity of the biosphere, which is generated by a very simple code of only 4 letters. And in some sense, I believe that this also happens in natural languages, where a literature masterpiece can be expressed in an alphabet of only a handful of symbols. Yeah, so why should this alphabet be so expressive? So what I'm trying to ask is, why is this the case that simple systems and simple rules suffice to generate so much complexity? So if you imagine some diagram where you consider the microscopic complexity of your system, which is empowered with some additional variables, and you consider what this system can express or simulate, then naively, you might expect that the more complex the system, the more expressive it is in some sort of behavior like that. But actually what happens is that as systems become gradually more complex, they undergo a very sudden change of functionality, after which they can explore all complexity in their domain. And this is called the jump to universality. And well, in the words of David Deutsch, or the words I'm borrowing from David Deutsch, this puts these systems at the beginning of infinity. And so this jump to universality has several features, as I see it. The first one is that the complexity threshold where it happens is very low. So very simple systems can already jump to universality. The second one is that it encodes some sort of explanation about the system or some sort of deep reason as to why this happens. I have several examples in mind, but I cannot explain it any better than this. And the third one is that it can only happen in digital systems because only these are capable of error correction, and this is crucial for exploring all complexity. So this has led me to propose a sort of principle, which I call universality everywhere, which says that essentially every non-trivial system is capable of exploring all complexity in its domain. So this explains in some plain words and in an intuitive manner why everything is so complex. So obviously this is the case for the examples I showed you at the beginning. First of all, the rule 110 for cellular automata, it is well known to be computationally universal, so it is beyond the jump to universality. It has jumped to universality. It's also the case for the 2D Ising model with fields for a slightly different notion of universality, and that's precisely the point of what I want to do. I want to compare these things rigorously. It's also true for the feed-forward neural networks due to the so-called universal approximation theorem. By the way, I forgot to mention that restricted Boltzmann machines have a similar notion of universality in order to approximate probability distributions. And the most famous and well-understood example is that of Turing machines, of course, which are universal for computation if you believe in the Church-Turing thesis. So in all of these cases, we see that there are actual and auxiliary variables. So my actual variables are denoted like with black dots, and the auxiliary ones were gray dots. And the story is always that the auxiliary variables are used to encode a description of the model that is to be simulated. Okay, so if you want your universal model to behave like one particular model, I call it the target model, you need to encode the description of the target model in the auxiliary variables, in these additional degrees of freedom, typically in the form of a distribution of couplings. So in this sense, universality is a statement about the power of simulation. As I see it, it's an extreme example of the power of simulation. It says that simple things with additional variables are already capable of exploring anything. And it is the beginning of infinity. And in fact, this book is super inspiring and brings some of these ideas and some of these principles to yet another level. And I can only encourage everyone to read it. So my goal is to understand this underlying phenomenon of universality. I want to do that by establishing rigorous links among these fields, in particular between spin models and neural networks on the one hand, and automata, that is to say, Turing machines on the other hand. And I'm hoping that from automata, which are linked to formal languages, I'll be able to kind of step to natural languages. I'll say a few more words in the outlook, and I'd be happy to take questions, but there's not much more I can say at the moment. And so as a first step to compare these notions of universality, we need to describe spin models as automata. That is to say, we need to put the objects of study in these two fields at the same level. This will allow us to compare rigorously the notions of universality in these two fields. That's what I'll do in this talk. And I'd also want to talk about one fascinating consequence of universality, which is undecidability. But first of all, let's see how we can describe classical spin Hamiltonians as automata. So this is joint work with David Drexel, who is a master's student in my group. Actually, he just finished last week, and it can be found on the archive, the latest version, like 10 days ago. So what we do is we associate classical spin Hamiltonians to a formal language and then classify this language in the Chomsky hierarchy. For example, a classical spin Hamiltonian will be a map from a spin configuration of n spins to an energy for all n, so for all lengths of this spin configuration. And the formal language will be the set of pairs of the spin configuration and the corresponding energy, again for all n. Okay, so there will be infinitely many elements in this LH. For example, so the 1D Ising model will be the map of spins S1 to Sn to an energy. So this is a number, the sum of the product Si times Si plus 1, Si is plus minus 1. This sum runs up to n minus 1, but we will consider this map for all n. Then there will be an associated language, which will be the set of pairs of the spin configuration S1 to Sn and the corresponding energy, again for all n. And from there, we will prove a theorem that says the language associated to the 1D Ising model is deterministic context-free and not regular, for example. Okay. So what I'm trying to emphasize here is that the association between or the correspondence of a language to a Hamiltonian is not unique. We will investigate some of this lack of uniqueness, but once the formal language is fixed, then its classification in the Chomsky hierarchy is unique. It's a theorem. Okay, so again, spin Hamiltonians, formal languages, and these themselves are in one-to-one correspondence with automata, namely the automata is said to recognize a language if you give it a string and it can tell whether that string is in the language. So for formal languages, we have this Chomsky hierarchy. The most complicated or difficult ones are called recursively enumerable. The simplest ones are called regular. And there's an associated automaton that recognizes each kind of language. Well, we prove that local 1D spin Hamiltonians correspond to deterministic context-free languages, local to the spin Hamiltonians to context-sensitive languages. This is also true for higher dimensional lattices. 0D Hamiltonians, which we see as a subclass of 1D Hamiltonians, which are in some sense holographic, I will explain this, are regular languages. And only highly unphysical spin models, namely totally unbounded spin models, which I don't think they even deserve the name spin models because there's no local term. Only these correspond to recursively enumerable languages. Namely, only these need to be recognized by a Turing machine. All other kinds of spin models are recognized by weaker forms of automata. Okay, so I'd like to be slightly more precise. This will only last like 1 or 2 slides. So how do we define a local 1D spin Hamiltonian? So first of all, we have a local term, little h, with k-body interactions. Now, k is fixed and independent of n, the system size. For example, k could be 2 in the case of the Ising model, but in general, it could be 50. It doesn't matter, it's fixed. And the image of little h is in the rationals. Now, a local 1D spin Hamiltonian is big H will be a sum of these little h's, a sum of these little terms, okay? For example, the first term h will be applied from spin 1 to k, the second from spin 2 to k plus 1, and so on, up to n. And like this for all n. Then we rescale and shift h so that its image is in the naturals. This is done so that we can express the energy in unary. The language associated to this Hamiltonian is then defined to be the set of all pairs of Sn, some separator, doesn't matter, and then a unary expression, so unary times the unary expression of the corresponding energy for all n again. And this other thing is not important, just some other separator. And then theorem L1D is deterministic context-free and not regular. Proof, use the pumping lemma to disprove that it is regular, pumping lemma for regular languages. and on the other hand, provide a deterministic push-down automaton recognizing L1D. And the code of this automaton is also submitted, has also been submitted to the archive. Yeah, and we have many pretty impressive figures that, that David made in our paper, so I would encourage you to have a look if you're interested. I can also give you the intuitive idea as to why this kind of machine is required to recognize this language, but in the interest of time, I'll just go on. Yeah, also an explicit representation of the automaton. Okay, and for 2D, we proceed analogously, but obviously in this case, we prove that it's context sensitive and not context free. And we also provide the linear bounded automaton recognizing it, as well as the script. And I can also give you the idea, but maybe I'll just go on. And we also investigate the freedom of the map, namely how H is transformed into a language. First, by imagining that the energy is encoded in binary instead of unary. Now, we find that if the energy is written in binary, then the language is context sensitive of 1D spin Hamiltonians. So the complexity increases when the energy is encoded in binary, intuitively because binary is more difficult to read than unary. So this supports our choice of unary by default, because we want this to be a complexity measure. So it makes sense that the corresponding language is as least complex as possible. So with unary, we get a simpler kind of language. But we also imagine that we rescale H so that the image is now in the integers, but it is not shifted to the naturals. So there can also be negative energies. And in this case, it's very interesting because some local 1D Hamiltonians then behave as 0D Hamiltonians. So their energy only depends on a set of finite spins at the beginning and at the end. And the ones in the middle do not matter. And essentially, there's some kind of cancellation of energies or of the contributions of the spins in the middle. So perhaps not surprisingly, the corresponding language is regular, because you need a finite number of states to recognize that. So in this case, the complexity decreases when the energy is not shifted to the naturals. Somehow allowing for negative energies allows for some cancellations of energies, and some more interesting things can happen. But in general, we conjecture that it is uncomputable to tell whether a given LH is the least complex one, because this is very reminiscent of the Kolmogorov complexity. Okay, and for the Ising model, the most famous spin model, we find a different threshold in complexity. Namely, usually this model is studied from the perspective of the ground state energy problem, where the 1D Ising with fields and the 2D Ising without fields are in the class P, polynomial time, so solvable by a polynomial time Turing machine. And the 2D Ising with fields is already NP complete. Now, as a language, we find that the 1D case is easy and the 2D case is hard. So it's a different threshold, and I think it's not so surprising from the perspective that our complexity measure does not only consider the behavior around the ground state, but the whole function, the whole Hamiltonian. Okay, and I'd very briefly like to say a few things about what can go wrong if one tries to talk about oneself. Namely, when we look at this diagram of universality, I see undecidability as a consequence of universality. Namely, undecidability is what happens when you do self-reference and negation, as when you say, I'm a liar, and if you try to decide if I'm lying or not, you'll conclude that I'm lying if and only if I'm not lying. So you cannot solve this from within the system. So talking about principles, my principle that there's universality everywhere kind of implies that there's also undecidability everywhere. I've written an essay explaining these ideas for FQXI.
All right, so yeah, so the punchline of all of these undecidability results is that no system can talk about itself. So by system, I'll mean a set
And by talk, I mean to describe an attribute of the set. That means to give the element of the power set that contains, let's say, the elements of the set that have that attribute. So for example, consider a finite set with only 3 elements, A, B, C, and well, its power set is the set of all subsets, and consider the attribute not being C, then the corresponding element of the power set would be that one containing A, B. Now, the trouble with trying to describe your own power set is that you'll never be able to do it, because no set can be put in one-to-one correspondence with its power set. In other words, there is no surjective map between a set and its power set. And for finite sets, this is obvious because the power set, its cardinality is 2 to the cardinality of the set itself, so that's obviously different than the cardinality of the set. But for infinite sets, it may have worked, but it doesn't work, as Cantor showed. And the reason it doesn't work is because of self-reference and negation. So if you wrongly assume that there is such a surjective map, you can always build this attribute of self-reference and negation, and this will always be outside the system. So this property of I'm a liar can never be captured, meaning can never be understood from within the system. And this idea can in fact be made very general and precise, in fact in the context of category theory. But if you're new to this, I would recommend you to have a look at this book. It's a popular science, very readable and very enjoyable book. And what I'd like to stress is that this argument is very far-reaching because it says that no set can be put in one-to-one correspondence with its power set. So from a set, you can build its power set. This will be more expressive or stronger. And from then, you can go on to the power set of the power set. And from then, even further on, and so on. And this doesn't end. So this doesn't stabilize, let's say. And yeah, kind of adding the problematic sentence, I'm a liar, will not help, because as soon as your system is expressive enough that it allows for this self-reference and negation, then somehow the system is doomed and there's no easy way to fix it. And I'd like to emphasize that it's very far-reaching and very transversal, so it can be formulated in many domains. In essence, as I said, it's nothing but the liar paradox. But you can also formulate it by saying this sentence is false, or Russell's paradox, so the set of all sets that do not contain themselves, does it contain itself? This is in the context of set theory. Or Cantor's theorem on the there is infinity, so that the infinity of the reals is larger than that of the naturals. It's based on the same idea. Or Tarski's theorem on the undefinability of truth, or the halting problem. So if you assume that there's a machine that solves the halting problem, you can feed its own source code and negate the result so that it holds if and only if it doesn't hold. So that's a contradiction. So therefore, no such machine can exist. Or Gödel's first incompleteness theorem. Or it can also be formulated in the context of semantics in some sense. So if heterological means that an adjective does not describe itself or cannot be applied to itself, like the word French, it's not a French word in English, then if you ask is heterological, you run into a paradox. This is called Greling's paradox, and that's just one more example, but there are more in other domains that you can find in these papers. So I'm trying to show you how broad this is, and the fact that undecidability or these paradoxes also appear everywhere. Definitely in all the systems that I talked about at the beginning. All right, so in conclusion, we have described classical spin Hamiltonians as automata, and we have used the Chomsky hierarchy as a new complexity measure of Hamiltonians, and we have shown that local 1D Hamiltonians correspond to deterministic context-free languages, and local 2D Hamiltonians correspond to context-sensitive languages, and in addition, the 0D case corresponds to regular languages, and only highly non-physical spin models correspond to recursively enumerable languages. so those recognized by Turing machines. What I want to do in the near future and midterm future is obviously to relate these notions of universality rigorously that I mentioned at the beginning, and to establish these two links. There are 4 open positions in my group, so 2 for PhD students and 2 for postdocs. So if you're interested, please get in touch, check our website, or let other people know who might be interested. We're looking for people. And what I hope to do is to move from formal languages, namely automata, to natural languages. I believe one has to be careful here in what respect so from what perspective of a natural language one is here trying to capture a property of universality, namely from syntax, semantics, or writing systems. I think this should be considered separately. And what I'm also trying to do is to extend some of this analysis to some notions of universality in biology, for which I'm enjoying very much some discussions and the future collaboration with Ricard Soule, who is a really interesting person. And what could also be done in the future is to bring all of this analysis to the quantum level. So notions of quantum universality exist for many of these worlds, and it'd be interesting to link them too. And I also want to study the consequences for undecidability, as I just mentioned. And what I also wonder is whether this entire framework could or should be formulated within constructor theory, because constructor theory is a theory about what can happen, not about what will happen. And it seems to me that the statements of universality are precisely statements about what can happen. And so I wonder if the existence of a universal constructor, for example, would supersede all of and provide a framework on which I could put all of these notions of universality in the various fields.